The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI Conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content. You can earn continuing education credits through ACI's online CEU program. Visit www.concrete.org to register. ACI Conventions provide an opportunity for networking and for keeping up to date with the latest in concrete technology and practices.
Our first speaker is Shideh Shadravan. She received her PhD from OU, I believe in 2010. I was her advisor. She's now a lecturer at Cornell University. Shideh.
Thank you very much, Dr. Ramsier. I am Shideh Shadravan. This presentation is about dimensional stability of type K concrete slabs on ground. I'm going to give you a brief background and some definitions related to slabs on ground, and then review some prior studies and research, and explain the purpose of our design, our research, and then our test method, test results, and finally the conclusion of what we found. About 2/3 of all the concrete in the world is used as slabs on ground, and many problems are encountered in practice with slabs on ground. As a huge amount of the concrete used as slabs on ground, the maintenance becomes a concern. One of the major causes of the maintenance needs for slabs on ground is the volumetric distortion of slabs, which is commonly caused by drying shrinkage. Drying shrinkage results the cracking in the concrete, and if drying shrinkage is not controlled, it can lead to serious serviceability problems and performance problems. So slab distortion occurs in all the slabs in ground. As an example of its impact, hundreds of millions of dollars are being spent to repair the slabs distortion. And grinding is one of the methods we use as a common method used to repair the slabs, but it is very expensive. For example, the state of California spent over $31 million to repair its road only in 1 year. So if we could prevent or at least reduce the effect of drying shrinkage, we can save money and time. So what is drying shrinkage? Drying shrinkage is defined as reduction in volume of the concrete due to loss of water. How this process happened, when the concrete dries, the free water of the concrete evaporates from top surface of the concrete. So the top surface of concrete shrinks, while the bottom surface and core of the slab concrete doesn't tend to shrink as much as the top surface. So a differential shrinkage develops through depth of the slabs. And in reality, shrinkage always is restraint. So the combination of the restraint and shrinkage causes the tensile stress develops through depth of the slabs. And if this tensile stress exceeds the tensile strength of the concrete, then the crack occurs in the slabs. So volumetric distortion of slabs on ground is one thing is actually curling and warping, and ACI defined this as a vertical movement of slabs edges and corners due to moisture gradient and temperature gradients. We have another definition in academic community that divides volumetric of distortion of slabs in two things: curling, which occurs due to uneven temperature condition, and warping, which occurs due to uneven moisture conditions. We use this definition in our research, and we focuses on warping, which is due to uneven moisture contents through depth of the slabs. So curling and warping could be upward or downward. Upward curling and warping occurs when the top surface of the concrete shrinks due to drier or cooler area at top surface compared to the bottom surface of the concrete. This is typical for internal slabs. And downward vertical movement of the concrete at the edges occurs when the top surface of the concrete expands due to higher temperature or higher relative humidity at top surface of the concrete. Now I'm going to review some of the prior research in this area. In 1938, Carlson had an experimental study on drying shrinkage of the concrete. He studied on 3 types of cement and 2 types of aggregate, and he showed that the moisture loss is greater at top surface of the concrete, and also the shrinkage occurs near the top surface of the concrete. So he concluded that when the moisture loss occurs at top surface of the concrete, a moisture gradient develops through depth of the slabs, and moisture gradient causes the shrinkage gradient, and shrinkage gradient applies the curling or warping moment to the slabs, into the slabs. In 1975, Carrier and his group studied on moisture content of a 10-inch pavement and 2 bridge decks. One of the bridge decks was formed on the plywood forms which were removed after curing the concrete, and one of the bridge decks was formed on metal forms which were stayed in the place. So you can see his result based on the first one. In your left is pavement, which just top surface exposed to the ambient, and second one bridges, which is both top surface and bottom surface exposed to the ambient, and the last one, the bridge deck, which was formed on metal forms and only top surface exposed to the ambient. So he concluded that, or he showed that based on his graphs, that moisture loss occurs at the top few inches of the concrete, which is exposed to the ambient. In 1987, Ytterberg studied on shrinkage and curling, particularly for internal slabs, and based on his study, the common causes of the shrinkage, cracking, and upward curling was high relative humidity of the subgrade, and also low relative humidity of the top surface of the concrete or ambient, and free water in the concrete. So he recommended, in order to minimize these cracks and shrinkage, we should use distributed reinforcement or shrinkage-compensating concrete or post-tensioning slab, or we can remove the factors that restrain the shrinkage. And in 1998, Weiss and his group studied on shrinkage cracking of a restrained slab, and he showed that the shrinkage reducing admixture delays the cracking, and high-strength concrete cracks more rapidly than the normal concrete. In 2007, Bissonnette and his group studied on drying shrinkage, curling, and joint opening of slabs on ground, and they show that the curling and joint opening occurs at early age, and they relate to drying shrinkage. In the other word, they said that rate of developing curling is proportional to the drying shrinkage. They also found that when they increased the reinforcement in the slabs, they noticed the cracks at midspan. So they concluded that high stiffness reinforcement can cause cracks occurs in the slab. Just a quick note that we follow Bissonnette test method in our research, And the purpose of this research is to improve our understanding of dimensional stability of concrete and also compare shrinkage and warping sensitivity of various materials such as Portland cement concrete, high-performance cement concrete, shrinkage-reducing admixture, and calcium sulfoaluminate type K. We simulated slabs on ground with 7 large-scale slabs on ground. The size of our slab specimens are 3 inches by 3 feet by 20 feet. And here is you can see the table of the concrete mixes we used for our research. 2 of the slabs were made with Portland cement concrete and 2 common types of shrinkage-reducing admixtures. We use Eclipse and Tetragard for our research, and also we use one of the test specimens was made with Portland cement concrete. That the only difference between this Portland cement concrete and the first 2 shrinkage-reducing admixture mixes is only shrinkage-reducing admixture. All the Portland cement concrete mix is all the same. So 2 of the slab specimens were made with Portland cement concrete and high-performance cement concrete or high-restraint concrete. And 2 of the slab specimens were made with type K shrinkage-compensating concrete, and also one of the slab specimens was made with rapid set, which gets its strength at early age. From now on, I'm going to take you through the method of our test, our research, to simulate the shrinkage. To simulate the restrained shrinkage of the slabs on ground. We used steel trusses at the ends. So we made a steel trusses and we welded these steel trusses to the plates. These plates were bolted and grouted to the existing slabs. So these steel trusses were welded at mid height of the plates, and also we welded 4 number 2 bar based on the ACI 360R minimum required temperature reinforcement. End of the slabs specimens are 9 inches. This way we restrain the slabs by casting concrete all around the steel trusses and for 9 inches. So this is the end of the slabs, and also we used 1 inch foam as a form, and also as a divider between our slab specimens and existing slab. Our slab specimens were located on the 4-inch moist compacted sand, and this picture shows the compacted sand, and also here is wetting the sand, and this picture shows a slab bed is ready to be filled with concrete, and you can see the bars and the chair we used to keep the rebar level at 1.5 inch depth of the slabs. 3 of the mixes were batched at Cornell at University of Oklahoma's facility at Fears Lab, and we use ready-mix concrete from the Lisi company for the 4 of our slabs specimens. Here is a picture showing pouring the concrete into the slab bed, and after pouring the concrete, the finishing crew finished the top surface of the concrete, and here is the finished slabs after all the work we've done. Then contraction joints were socket at 5 feet from the end of the slabs to provide the 10 feet long central test for our research. So the depth of these joints are 1 inch. We cured all the concrete slabs for 7 days with wet burlap and plastic sheet, and after that we removed the foam all around the concrete, and then we placed the flexible 1 inch baker rod in 2 layers all around the concrete slabs specimens. So in this picture, you can see our slab specimens are located on the ground, and the top surface are exposed to the controlled environment. This picture shows the overall plan view of the slabs. You can see the You can see the location of the joints that I already told you. It's a contraction joints placed at the 5 feet from the end of the slabs to provide a 10 feet long central test, and also we attached some demic target to joint opening and mid-span to measure the surface strain. I'm going to go through this later in our test results. And this is showing this picture showing the profile of the slab deformation due to warping, and you can see this is the location of the warping, and I wanted to show you the end restraint of the concrete in here in this picture. Now I'm going to review some of our data from our research, and we took some samples from each batches to test ASTM C157 and C878, which are unrestrained shrinkage test and restrained shrinkage or expansion test, respectively. I'm going to review some of the data we got from this test, ASTM test. I wanted to show you the expansion of calcium sulfoaluminate at first days of the curing, comparing calcium sulfoaluminate with one of the shrinkage reducing admixture in this picture. In this graph shows that the calcium sulfoaluminate has a 0.09% expansion at the first curing week, and then shrinkage reducing admixture has 0.02%, which is about 4 times calcium sulfoaluminate expansion is about 4 times greater than shrinkage reducing admixture. In this graph, I wanted to show you the calcium sulfoaluminate expansion that you already saw, that is 0.09% compared to the high performance concrete, which is about 0.01, and its calcium sulfoaluminate showed 9 times expansion greater than high performance concrete at the first week of curing. And in this picture, in this graph, I wanted to compare the Portland cement concrete with shrinkage reducing admixture. You can see a minor impact on shrinkage at short term and long term using shrinkage reducing admixture in our tests. As I mentioned before, we attached some demic target at the joint opening and mid-span to measure the surface strain of the concrete slabs on ground, and here is the gauge we used to measure this. And now I'm going to review some data we measured at mid-span of the slabs and located on the slabs and measured at the mid-span. This graph shows the Portland cement concrete and shrinkage reducing admixtures we used, both of the shrinkage reducing admixture for 28 days, which is 21 days after of drying. So you can see the shrinkage reducing admixture delays the shrinkage at these first few weeks. And here is showing the slab results for the 600 days. And showing that there is a minor reduction on shrinkage at early age and almost at long term for 600 days of results. Now I'm going to review some of our joint expansion results measured at joint opening from the demic target. I already mentioned that, and this is actually showing the measurements of the crack growth at the joint opening, these results. Here is the graph for all the slabs and mixes we use, and showing the joint expansion. Here is showing that at the top we have high performance concrete, which is showing that the largest expansion, and at the bottom line we have a shrinkage compensated concrete, which is showing that a very low shrinkage or joint expansion for our slabs on ground. This graph shows the joint opening, joint expansion for the normal concrete. As you can see, there is the shrinkage starts at early age for Portland cement concrete, and also this shrinkage or expansion continues for a long term. We measured this for about 600 days, and we still notice the joint expansion continue after about 2 years. Here is showing the Portland cement concrete, two types of shrinkage reducing admixture joint expansion, and again you see the delays in shrinkage using shrinkage reducing admixture, and also you can see the shrinkage in these two types of shrinkage reducing admixture continue for a long time, for about 600 days of our measurement. In this graph, I wanted to show you Portland cement concrete versus the shrinkage reducing admixture we use. And you can see if we just compare this, showing that these graphs actually like they are parallel with an offset by the initial shrinkage, or we can say that these graphs are, with exception of the first few weeks, are positively correlated, and that they have the same trend. If you look at this trend I wanted to show you. This graph shows the high performance concrete, which again you can see the early age shrinkage or expansion joint, and also it's continued for a long time. After 600 days we had a still joint expansion for this type of the concrete. And in this graph I wanted to show you, compare the high performance concrete and Portland cement concrete, and as you can see the shrinkage of the high performance concrete is more rapidly than the Portland cement concrete or normal concrete, and also the joint expansion is wider or larger than normal Portland cement concrete. And now you can see the joint expansion for type K calcium sulfoaluminate. There is a very slow joint expansion at the early age, and also we almost didn't notice any additional joint expansion after a long term. And in here I just brought the table for joint expansion from that graphs that I already showed you. It's after 4 days. You can see all the expansion for all of the concrete we used are greater than type K. For example, Eclipse showed that the joint expansion is about 2 times greater than type K, and Tetragard showed about 2.5 times its joint expansion is greater than type K, and Portland cement showed about 3.5 times larger joint expansion in compared to the type K, and also high performance concrete showed about 4.5 times larger joint expansion than type K. Just the conclusion of my presentation is typical Portland cement concrete, high performance cement concrete, and shrinkage reducing admixtures continue to exhibit joint expansion at approximately 2 years. And as I mentioned before, this joint expansion was the crack that we measure at the location of the joint opening. And we also found that the ASCMC 157 does not provide an accurate method to predict the behavior of material used in a slab on ground. We compared the results, and we found there are significant differences between the results. We also found that the shrinkage reducing admixture have a minor impact at both early age and 600 days, and almost very close to Portland cement concrete. And finally, we found that the shrinkage-compensating concrete is extremely stable with little or no long-term shrinkage or cracking. This was the results at the early age and also for approximately 2 years. At the end, I would like to thank all the supporters. All the supporters of this research. This project would not have been possible without the help and support of Oklahoma Transportation Center and CTS Cement Manufacturing Corporation and University of Oklahoma, where the research was conducted. And my special thanks to Dr. Chris Ramsier, who I am grateful to for his help and guidance. Thank you very much for listening to my presentation. I would be happy to answer your questions. Thank you.